So this is paper 2, which is what you all asked for. So what we need to be doing is making sure that if you're making flashcards, please make sure that you get down the keywords, because this is so important to making sure that you get all of the marks available to you. So anyway, let's get going. So the first question is, what is the precondition for binary search? The list has to be sorted. In a binary search, it has to be sorted. Linear search is the one where it starts at the very first item and works its way along. Essentially, with the linear search, this is quite difficult to get 4 marks on it. Exam technique, make sure you are, making 4 solid points to get that. So starts at the very first item, checks to see is the item you are looking for. If it isn't, it moves on to the next item in the list and checks this one. This will go through the whole list in order. That's a really important thing, because you can't just say like it goes through the whole list, because it's a little bit vague for the examiner, and either finds the item and outputs it, or gets to the end and says item not in list. Okay, that's probably a little bit more than you needed there, but that's all of the points that you'd need for that. Okay, so in this one here, we've got, so it says identify 2 variables in the function use words. So we've got number of words, which I'm going to make sure, because there aren't any spaces, don't give them any chances to not give you the marks for it. So make sure that no spaces, and also capital letters where they are. Contents. And then what it says here is you've got what's the difference between by val and by reference. So by val is where it makes a copy of the original value, and by reference is where it changes the original copy or original value. So it's to do with, if you do Python, you don't really have to do this that often, but in other programming languages you do. What happens is when you're passing the value, it potentially takes it from it either makes a copy of it and then uses that copy, which is by value. By reference, it's actually referencing the actual value, so it changes the original value. So later on, the values might be different based on the different, whether you use by value or by reference. Okay, so it says rewrite the function use words to use a while loop instead of a for loop. The function header and close have been written for you. Lovely. So what I'll do is I'll put that on the same page so that we can see it. And a lot of this is going to be actually quite similar in there. It's just we've got to be careful about how we're going to get the loop to execute. Put that T, there we go. Perfect. Okay, so let's have a look. We used by wrap. We've already done that, so we don't need to go on to that. So we're going to need contents, so we're going to put that in there. So contents, that's going to be exactly the same as before. Then this is where we're going to go while. Okay, so with this one here, we'll go count, because we'll probably have to create a count less than. In this one here, this is going to be number of words. So essentially what we're going to do is almost create a for loop out of this while loop. So we'll do number of words. And then the same part there is going to be, okay, so we can do contents equals contents plus words, square brackets, count, plus, and then we have to put the little speech marks at the end there, which that's going to be the same. Make sure you get the space in there as well. The for count, we are going to need it to go up though. So we are going to need to make it go count equals count plus 1. And I've just thought we have an initialized count, so we're going to need that as well. So we're going to do count equals 0. And then that will loop round, and this one, so that's all there. And then after everything that we've done this, we actually need to return content. So I'm just writing this in Python, so I don't need to put end while, but if you're writing it in pseudocode, you would do that. And you're just going to put return contents and make sure you've done that. Okay. Give one benefit and one drawback of declaring an array as a global variable instead of a local variable. So essentially with this, it's, so give me one, global variable instead of a local variable. So you don't need to pass as a parameter, which is, if it's a global variable, you can use it in anywhere. So that can sometimes be a benefit, as you don't actually need to think about passing it as a parameter. It can cause more errors though. So it can cause errors in the program, and it's difficult to locate where the problem is if you have lots of global variables. So with this, if you use lots of global variables, it actually makes it very difficult to locate where all of the problems might be. If you use local variables, you know that everything is sort of built into each other, so that you know where in that particular function, if there's an error, it's going to be located within there. So it makes it easier for error checking. So yeah, that's what I'd go for that one. Okay. Describe one feature of an IDE that can be used to help write the program, and one feature that can be used to help test the program. So to help write, that would be things like syntax coloring, auto-completion. Syntax this will change color when you use certain keywords, and this will change color when you use certain keywords, and when it doesn't, this helps you to notice you may have made a syntax error. Testing is something like a variable watch window. You watch a variable throughout the whole program to make sure it runs as expected. Give two benefits of writing programs with reusable content. So it's going to speed up development time, as you don't need to spend time making it. If it's got reusable components in there, you also know that less error checking, as normally the program has been tested to make sure it works. So it kind of speeds up development time. It's going to be less error checking. So it's just going to generally be good in those two areas, and they work quite a lot. Those two answers. So speeds up development time, less error checking, can help out quite a lot in those ones. So speeds up development time, less error checking, more reusability in terms of that. Okay, so we have got we've got binary tree, and it says identify the root node in the binary tree. So the root node is the one at the top. It's kind of like the reverse of a tree, because a tree obviously grows from the ground up, but think of this one here, the top's there. So 2005 is going to be the one there. The leaf nodes are the ones on the end. So if you picked, so we can go for that one, 1952. And then we've got 2000 there as well. The other ones that you go for as well as 2100, 2560. It's just got to be at the end of a tree, essentially. So any of those ones. Okay, so 4 students have been added to the binary tree. Let's have a look at this one here. So we've got adding 1420. So it's, with binary trees, if it's less than, it goes to the left. If it's bigger than it, it goes to the right. So less than. And then you ask the same question again. So is that going to be less than? And they can only have 2 nodes. And then less than. So that's going to go here, which is going to be 14. Sorry, it's a little bit difficult to do it on here. So that's going to be 14 and 20. 2050, so bigger than. Less than, less than. So that's going to go it's going to go less than here. So that needs to go to the left of there. 2780, so it's going to go greater than, 780. And then finally we've got 2600, so greater than, and then we're going to go to here, which is then less than, so then it's actually going to go here. So I've brought this onto this page so that you can kind of see how it works. So essentially what the question's asking us to do is to traverse the binary search tree. And what we've got to do is we've got to compare breadth first and depth first. So I'm going to go through depth first because I think that's the more challenging one to understand. And it's a 9-mark question, this one. So the way in which we've got to think about this is it's the same pattern as we always do, which is like describe it, apply it, and then evaluate it at the end there. So do we understand what breadth first and depth first actually is? So what we can do is we can just quick description, talk about the nodes that are visited. As I said, the depth first one is a little bit more challenging. Depth first is this idea that what it does is it's kind of so the reason it's called that is because it starts at the bottom and kind of works its way along. So it's going to go 14, so it's going to go to this one, 1500, 1952, 2000, work its way around the outside. So it kind of does this tree first. So it starts here, works its way up, 1952, 2000, 1985, and then visits the top of that tree, which is 1920. Now here, so if you imagine, we've kind of done like this. 1985 there. Okay, this is the part where people really find it quite hard, and this is just practice, just going over lots of different examples of this. We then have to visit the bottom left of the next tree. Okay, so we've got this tree over here. So essentially what we want to do is we want to come down here. I mean, you want to start there. So we've visited all of those nodes, and then what we're going to do is we're going to come across here. So we're going to go up to here. So 2050, 2100. Okay, it's very tempting to cut across here, and then what you're going to do is visit the bottom of this, 2600, 2780, 2560, 2350, 2000 and 2005. As I said, I know that that's like, it looks crazy, but I would say the idea behind it is that we finish up on the root node. That's the last thing that we're going to do, and then the first thing that we've got to do is we go to the bottom left hand corner of the tree, go to the bottom left hand corner of the other tree, and you kind of work your way around the outside of it. So if we describe that, so we're going to say that depth first is where we start at the bottom left hand corner of the tree, of the left hand tree, and we work our way around the nodes until we finish at the root node at the end. And then probably what I would do to get the application marks is I would actually write down the nodes and the order which they're visited in. So 1420, 1500, 1952. So remember, it's working its way around the outside. 2000, 1985, 1920. And then we're going to jump to the bottom left of the right hand tree. So then we're going to go 2050, 2100, 2600, and then we'll go around the outside, 2780, 2560, 2350, because we're going around the outside, and then finally 2005. Okay, now breadth first, I generally think is a bit easier to understand in this one. So we've got breadth first is where you go through the tree in levels. You start at the root node, and then you go from the left hand side of each node of left hand side of the tree and work your way across. So that's, again, description, now application. So it starts at 2005 because that's the first node. So we kind of imagine this is like level 1. Then what you've got is level 2. So then what the next things that we're going to visit is going to be 1920, 2350. Then we've got level 3, which is going to be 1500, 1985, 2100, and you're just working from left to right. 2,560. Now, just be careful because, you know, in this case, it would have been better if what I'd done is I'd put the 1,420 at the same level as this, and also the 2,050, the 2,780, because it kind of is a little bit misleading because these ones here are all on the same level. Okay, so just make sure that you're working left to right, and then 2,600 should be the final one that we kind of go through on that one there. So 14 and 20, so it's all about the levels. 1952, 2000, put this over here, and then we've got 2050, 2,780, and then finally 2,600. Okay. Now, with the evaluative points, so obviously you get a lot of marks there for just going through and actually knowing what those ones are going to be there. And you've just got to have a couple of evaluative points which you can kind of talk about and maybe think to yourself about how, you know, a few things that you can say about them. I would say I'd maybe aim for at least 2. And then if you can go for more evaluative points after that. I would just have 2 solid points that I could make about both of them. And then if you can think about some more, get those in there. But remember, you're going to be having about, I would say, 10 minutes that you want to be spending on this. So if you think about it, if you're running way over, okay, just make 2 solid points. If you finish the paper, then go on with the rest of the paper. If you finish early, you can always come back and make some more points in this. So I'd just be going that breadth first, because it starts at the top, is more efficient trying to find the value near the top. And then the inverse is true for depth first. So depth first, because it starts at the bottom, it is much easier to find, or much quicker, I should say, rather than much quicker to find values that are near the bottom of the tree. Okay, so going on to the next one. A bubble sort will sort an array of 50 integer values into called numbers of array. State why integer values are stored in an array instead of separate variables. We can reference all 50 values using only one identifier. Okay, so that would be the thing about the main advantage of using arrays and lists. This is the bubble sort algorithm. So for here, it's going to be 50. Okay, and then we've got essentially a do until, which will always execute essentially once just to check it, and then it'll check the condition at the end, which if you're familiar with Python, this isn't something that we use in Python, but still, it's still going to be, you know, still something that you need to be familiar with. So it's almost like a back to front while loop. So the values that we're going to use are, we need to subtract 2 away from it on this one here. There are, I'll put out a video about all of the different algorithms on sorts searches. Also, we do have a little community, which is, which I'll put some links in the description as well, which we talk about all of these things, go through the algorithms, and essentially you can just make flashcards about this and just learn these, all of the big sorts that come up, quick sort, merge sorts. But yeah, I'll put a link about that. With this one here, this is going to be temp value, which is going to hold the value temporarily. And yes, sorry, I need to put a capital V there, so just be careful on like capitals and things like that, where it's up at the top there. So temp value is going to be a placeholder from when we're swapping things over in there. This one here is just obviously, so this is where we're comparing a value in a bubble sort with how the bubble sort works. So if the value, we want to swap this over. So if the one before it is greater than the one immediately after it, we need to swap this over. So we're going to say this is equal to the other one. And then what we're going to do is then you essentially just put the value in here, which is going to be temp value, which is just going to temporarily store it. There is actually ways in Python now where you can do that all in one go, which is kind of, because yeah, Python's been updated so you can swap it over on one line, which is quite easy to use. But you still need to know how all of this works, because as you can see that they do put pseudocode and things on in there. So those are all of the different values there. Okay, so we've got a section here which is going to be about merge sort. So it says show how merge sort will sort this section, going through this. Now, with this, it says show how a merge sort will sort this. I would probably put descriptions, and I would put the numbers in the order in which it goes. So with all of this, I would say split all of the items up into fours. So obviously you do split them up into fours, so it's going to be like 2, and this isn't anything to be doing with sorting them, because you have to get them individual to start with. So there's those over there, and I make a really clear distinction that they're together, and then these ones are together. Split into pairs. Just making sure it's really clear that you've got them all split up. So 2 and 12, 1, 9, then you've got 3 and 5, and then we've got 15 and 7. Okay, split into individual values. So then you've got 2, essentially 2, 12, 1, 9, 3, and 5, which is this is sometimes what people forget. Sorry, it's automatically putting those dots in there. You don't need to put those in there, but for some strange reason this is doing it. So you've got individual values. Then it's this idea of once they're all split up like that, then you need to sort them as you're pairing them back up. So pair and sort. So notice what I won't do is I won't pair them and then sort them. It's done automatically. So 2 and 12. 1 and 9, I mean, they're already kind of sorted because they're in the correct order. 1 and 9. 3 and 5. So it's only the last 2, which is actually, they'll get swapped around. So you'll see here, I don't pair them and then swap them. It's done simultaneously. And then let me just move this up so that you can see it. Pairs into fours. Sort, so then that's going to give you 1, 2, 9, 12, and then over here then what you've got is 3, 5, 7 and 15, which is kind of the same order, and then you just pair the fours up into 8s. Pair the 4s into 8s, which is now sorted. So then essentially it's just going to be a sorted list. So 1, 2, 3, 5, 7, 9, 12, 15. So it's just one of those ones where it's just be extra careful, make sure that you've got 8 numbers at the end. Yeah, that's all good. And just making sure that you're going through all of those different stages there with that. Okay, so on to the 12 marker, which is talking about each of the different algorithms in terms of insertion, bubble sort and merge sort. And we need to talk about the big O complexities and the suitability for each of these with sorting 10 values in there. So first thing, I'm just going to describe what each of these are. So bubble sort, take the item the left and compare it with the one next to it, and then swap if larger, or move on to the next item and repeat this process until the largest item at the end of first stage, and then goes back to the start and repeats process. So and then we've got insertion, is where we take the first item and place in new sorted list, and then repeat going through rest of list. Merge sort, where we split the list up and then pair up and sort as we are going through the list. So I'm just making sure and sort as we're going through the list. Okay, so I'm just describing, just making sure that they understand that I actually know what each of those sorts are. Then what I'm going to be doing is I'm going to be talking about how we are going to be, essentially with this one, we want to talk about the big O notations, which again is just, do you know what the big O notations for these are? You can obviously talk about the average big O notation, because obviously the best case scenario and worst case scenario. In this case, it isn't a very big list, so I would maybe be tempted to talk about the big O notation in terms of a best case for insertion and bubble sort, because there isn't many items. These aren't very good when there is a large amount of items, especially bubble sort is really bad. So I'd even make that point, and maybe you can make that later on, is the big O, which this is obviously the application part. Now, the big O notation, amount of searches in a best case scenario for insertion and bubble is going to be ON, which would fit this scenario because there are not many items in the list. Merge sort will always, well, not always, but on average, will have a n log, so n log n big O notation. Okay, so you need to just specify to them, do you actually understand what the what the example of this is going to be and what the big O notation is? Okay, and then what I would start doing is, once I've applied it, so I get those application marks, what I'd then be doing is I'd be thinking to myself, okay, let's start making some evaluative points. So I'm just going to move this up, and I'd start talking about, you know, those things that I was saying earlier. So these aren't very big. This isn't, I should use proper English. This isn't a very big list, so may make sense to use insertion or bubble because it is a small list and they perform poorly on larger lists, but on smaller lists you do not need to use merge sort and use a lot of memory. Or merge will always use a large amount of memory for any search, and because this is a small list, it may be preferable to use insertion or bubble. Okay, so again, make your points. Because you've got 12 marks, I would say just you've got about over 10 minutes to see if you can answer these questions. If you need to come back and then make some more evaluative points in there, is because you may want to actually say, well, merge sort doesn't need absolutely excessive amounts of excessive amounts of memory because of all of the sort of like having, in really large lists, they would have huge amounts of memory, and this is a small list, so you actually maybe want to counter that point there. But I'd just be maybe thinking about, use the time available, and then don't run out of time on the rest of the paper, so then start going through that. So it may make more sense, in, as I said, that you're talking about how the memory is there's going to be more memory usage in merge sort and in bubble rather than in bubble sort and insertion sort. So it might actually be better to use one of the other two because it's a smaller list, but you could then also make the point that actually it's not going to use huge amounts of memory. So you could talk about that, have more of a discussion, but remember, you've only got a certain amount of time that you can actually use on this. Okay, so with these ones here, let's just get some definitions down. So removal of unnecessary necessary parts to focus on what's important. Decomposition, breaking down into smaller problems. Give 3 things, the abstracted things. So it's like, what things can we take out which aren't super important? So you want to be able to focus on the speed, and actually maybe another thing is like focus on the weather conditions is probably what you want to be training people in those aircraft simulator to do. Removal of building and nature details, because obviously it's not super important. Like it's like really realistic. You maybe just need like a square block. The reasons for this is normally to protect the hardware. So it's like processor, limit the amount being used on processor, limit amount being used on memory. Okay, so in terms of caching, okay, so this is it's one of those ones because it does feel like this should be on paper 1, really. So it's just what with caching. Remember, it's we store frequently used instructions. So we store frequently used instructions and data. So you don't to fetch it. So this could be, so then what I would do to get the application mark in this one is I'd probably talk about how, something that is going to be used often in this actual scenario. So you'll get 1 mark for just saying what it is, a 2nd mark for applying it. So this will be the weather, storing the weather conditions, or yeah, I mean you could say maybe like the level as well. So or the whatever it is. So the in the simulation, storing the weather conditions in there. Okay, storing the weather conditions for that run through. Okay, so that's all good. Okay, so we've got so with this one here, we've got our graph, and we're going to say state one way. A directed graph is different to an undirected graph. State. This may seem quite obvious, but the edges can go both directions in a undirected graph. In a directed graph, they only go one way. State one way a graph data structure is different to a tree data structure. So a graph has cycles and a tree does not, which just essentially means that you can get round everywhere in a graph. It says give one reason why it's a visualization. So it's essentially it's this idea that you've got like symbols and edges are representing possible connections between nodes. Cool. Okay, so that's all good. Okay, so this one here, what we've got it's asking us to do Dijkstra's shortest path. I think it's asking us to show how Dijkstra's shortest path can go from node A to, let me put this on. Okay, so on this question, what we're going to do is Dijkstra's shortest path algorithm, which is going to get us from A to H. So H. Okay, so we need to work out the shortest path of that, and we have to visit all nodes to do that. So what we're going to do is we're going to cross it out when we visited it, because we're going to start at A. And, you can write anything down that you need. I would, keep track of things that you're doing. So you can do A is equal to 0 because we haven't travelled anywhere and there's no previous node there. If it's helpful, as I say, cross it out. And then what you do is you put any nodes that are touching the edges. So from A, it's only B. So we're just going to put B is equal to 3. And that goes to the front of the priority queue. We do go through this quite a lot in the community, people, so you get a little group lesson and things like that where you can suggest what you need to do. So please do give us a message if that is something that you're interested in. I'll put a link in the description. So that's the first thing that we're going to do, and then we will put B, and we just need to make sure that we put the previous node, which is going to be A. put a capital A there. Now, the next thing is obviously we're going to go visit E and D from there. E is going to go to the front of the priority queue because it's a shorter path. So we're going to put in E is equal to 6 because it's 3 plus 3. And then D is going to be 10. We're then going to visit E because that is the next shortest path. The distance travelled to there is 6. And the previous node is going to be B from there. Now, in this, from here, then what we're going to do is we're going to visit, so we have to go all of the places from there. So C is going to be, C is equal to 3 plus 3 plus, so that's going to be 13, because it goes 3 plus 3 plus 7. F is going to be 9, so that actually jumps to the front of the priority queue because that's the shortest route. And then D is going to be in the middle of that, so that D equals to 10. So if it does help as well, you know, you might have a bit of crossings out and everything, but you need to be organising your priority queue like that. So then that's going to give you that. F is where we're going to visit next. So that's going to be 9. And the previous node that we visited from there was E. Okay. So we've got that in there. Then once we've got that, so we've got that in there like so. So that's all good. Then from E, we're just going to write down all of the different things that we've got coming from there. So the only other thing there is obviously G that we can bring in there, which is going to be 3 plus 3 plus. So it's going to be 9 and 7. So that's going to be 16. So G is going to be 16. I'd probably do, so obviously D is going to be 10. C is going to be 13. So it's going to be like that from there for us. So next thing that we're going to visit is D, which is going to be 10. And the previous node for that one there, if we cast our mind back to there, is going to be B. Now that later on, it's actually going to be, well, I'll talk about C in a second because it's actually going to be E is going to be the previous node, not D, but I'll talk about that in a sec. So that's going to be B. It's going to go from there. C, as you can see, C is actually the same distance going from there, but because we went this way first of going through E, even though that they're the same, E is going to be the previous node that we're going to visit on that one there. Now D, going from there, you can visit H from D, which is going to be 21. So we've got C is equal to 13 from there. G is equal to, and remember the previous node on that one, because even though that they're the same, you do need to put that your previous node was E because that was the first one that we actually got there too. H is going to be equal to 21, so we've got it like that. And then we're going to take out C from the front of the queue, so then that's going to be C. As I said, it doesn't make any difference really that about that one. You could, I mean, it's always good to check. So C is going to be 13, and as I said, the previous node for that one is going to be E. You can always run a little check, so you can do 3 plus 7 plus 3, but it's just going to be longer to go to E from there. That is going to be 20 as opposed to 6, so there's not going to be any point in replacing that. And then what we can do is we can run going from G, which is actually going to be shorter going to H. So G in there is going to be equal to, obviously, 16. We're not going to replace anything, but you can see 3 plus 3 plus 3 plus 7, 16, add the 3, that's actually going to be better, isn't it? So when we go there, so H is actually going to be equal to 19. So what we've got here is, and obviously if you're doing calculations like this, the examiner can clearly see that you've done Dijkstra's shortest path. You haven't just wrote essentially all of the correct answers in there. So then that's going to give us G, which the previous node of going to that one is going to be F, because that's going to be the shortest path going to there. And then H is going to be G. Now, you can if you want to. You can obviously put like 21, cross it out and put D in there. I have seen that on the mark scheme. But I think obviously that this demonstrates that you've done it, you kind of calculated it correctly as well. So I wouldn't be too worried about doing that. But if you can remember to do that, that's going to be absolutely fine. So it is actually 19 and the previous node is going to be G from that one there. Okay. Now you will notice at the bottom there, you've got the path which is going to be going there. So essentially what you have to do is you're just going to write the way in which you go around there. So it's just this. So it's going to be A B E F A B E F, and then it's going to be G H. So you're just going to go A B E F G H, which is going to be the shortest path to there. A B E F G H, which is that is the shortest path there because we don't need to go to D, and then the distance is going to be 19, so that's going to be the final part there. So just make sure that you write that up there.